Okay, so today's presentation is going to be given by Hjalmar Lindstedt. He got his bachelor degree in Uppsala University, Sweden, and he's now doing, well, in engineering physics, and he's now doing the quantum track in the Master of Applied Physics here in TU Delft. Well, Hjalmar very much likes programming, and in the quantum field, he is very interested in hybrid quantum algorithms, so seeing how the classical processing and the quantum advantage can complement each other. So with this, I would like to give the floor to Hjalmar.
Thank you so much. Hello everyone, and happy everyone came here to watch this presentation. So this is not going to be about quantum algorithms at all, it's something completely different, but I hope it will be enjoyable nevertheless. So I will speak about this paper, which was published in Nature Photonics in 2016. And the name is Efficient Metallic Spintronic Emitters of Ultra-Broadband Terahertz Radiation. So a lot of words, I'm sure you will understand all of them at the end of today. Yes, it was very many authors involved in this paper on different locations, different universities. But I want to highlight one of them, and it's this man, Mr. Pérot. Peter was my professor in Uppsala, and actually a big inspiration for me to actually come to Delft and to do the quantum track. And so shout out to Pérot. Okay, so the agenda of today, we will start with some background about the Terahertz gap and the pursuit for emitters. We will then go through some theory of the spin Hall effect and laser-pumped spectrostructures. We will look at some applications and optimizations of this theory, and in the end we will have some discussion maybe. Okay. So let's start with the Terahertz window. So this is from Wikipedia. It's the different categories of the electromagnetic spectra. On the second one is the microwave, which is defined as, or I mean, this is loose boundaries, like it's not something, it's not a hard value, it's not a convention, but many people say it's between 300 megahertz to 300 gigahertz, which is 0.3 terahertz. So terahertz will be the base unit of today, which we will work in. And then the near infrared is the next one. And it's between 120 and 400 terahertz. So there is a gap here, which we also call the far infrared. And a subgroup of the far infrared is the terahertz region, which also differs a bit in definition, but in general they define it as between 0.3 to 30 terahertz. So this terahertz window is actually a bit hard. It's been like a mystery for many scientists for a long time, because it's hard to construct devices that can actually emit these wavelengths. And what can you do with the terahertz? Well, you can do some spectroscopy of big biomolecules with these wavelengths. You can also do some spectroscopy of condensed matter physics, and also for astronomy. The terahertz is an important wavelength. In this scenario, it's actually more about receiving and detecting emission, but I mean, they're connected. And also basically like scientific progress, like it's always good for us to learn more about something, even if we don't know what we will use it for today. So why is the terahertz such a rare bird? Well, it's bounded from below by the impedance of electronics. So this will be a bit of a stupid, not completely precise description, but I found this very simple model of an antenna online. So you have these three components in parallel, which basically are the dipole, which oscillate to shoot out this radiation. So very simplified model of the antenna. And we can recognize that when we put the frequency very high, the capacitors become basically wires. They have no resistance. And the inductors, they become like cutting, what do you say, like stops. And we get this thing, which cannot emit anything, like the dipole is equipotential and it's not connected like it just did. So this is like a limit, like a high frequency limit for the electronics. So on the other hand, we have the upper bound, which is optics. So we know how to construct many lasers. There are very many different versions and kinds of lasers, and actually the spectral lines and the transitions between energy levels and atoms are the limiting factor of this, as you probably know. So this was something I did. I took some data from Wikipedia and I arranged them in this logarithmic histogram. So it's not to be taken as like completely exact facts. It's more like a, how can I say, like just to show like a little bit like where are the lasers mostly located. And for example, we have the carbon dioxide laser, which is at 28 terahertz. It's one of the like lowest energy lasers, like most long wavelength, low frequency. And we also have the free electron laser, which is super nice but super expensive. It's these things you have where you accelerate electrons to basically the speed of light, and it's like it's not really something you can have in your home. And also we have some state-of-the-art emitters, which they are okay, they're not perfect. So this is in 2016, so I don't know, maybe there have been some more progresses since then, but this is what they mentioned in the paper. So we have the optical rectifiers, which is basically like a sort of filter for, not filter really, we can go more into detail of this later if we have time, but for example, this zinc, tellurium, and gallium phosphide, these crystals can actually emit in the terahertz region, but they are very weak, between 5 and 10 terahertz. And we also have the photoconductive switch, which is another device. Also can do something in the terahertz region, but it's very weak after 3 terahertz, basically. And then we'll also talk a bit about spintronics, which is electronic devices. No, it's not electronic devices. It's another thing than electronic devices. Because electronic devices utilize the charge of electrons to basically do work, send information, as you know. Spintronics, however, utilize the spin of the electrons. So it's much more novel, much more complicated, like easy to collapse, stuff like this, but it has some very interesting potentials. Like, for example, it's more energy efficient. You don't have the ohmic heat dissipation in the same way. It's actually used in, for example, CD disks. You have this magnetized, like the ones and zeros in a CD disk are stored as magnetized directions, basically, which is spin. So it's already used. And we also have some spin-based quantum computing here in Out, for example, which is another thing to apply this to. Okay, so there's some background. So now we'll go into some more hardcore theory. So I will skip through this one actually. It's very basic, like the current, how you model a current. But you can look at this final expression, which is basically electron flow. So it's current density divided by the electron charge. So essentially it's a measurement of the number of electrons coming through an area. Okay, so then spin currents. So charge current, we all know, transport of electrons. What is a spin current? So basically the key idea here, so we continue with this notation of the charge flux, the QI. So the difference between a charge flux and a spin flux is that you actually need 2 indices to describe the spin flux. Because charge only has one component, x, y, z. Like it's the direction of where you travel, and also a sign, like are you positive or negative. However, the spin flux actually requires 2 indices because of the polarization of the spin. So if I travel like this, for example, I have one direction for where I travel and one direction for my polarization. Everything okay? Yeah. So then we can define these equations actually. So we have for the charge flux, we have one term which basically describes the force from the electric field pushing the electrons. And we also have the diffusion process, basically, like charge relaxation, which is this gradient of the conservation. And you just multiply this pj factor to get the, basically to get the, so it's basically the spin direction vector. Okay, so let us then go into the spin Hall effect. So this is an effect which you only can understand if you understand the notion of spin currents. So it's a relative to the anomalous Hall effect, which is something we will not cover today. And it was predicted by Mikhail Diakonov and Vladimir Pérot in 1971. And it is a relativistic phenomena. It is due to spin-orbit coupling, and it describes a conversion and a connection between spin current and charge current. So these two phenomena are not always independent of each other. They have some sort of connection. All right. So yes, it describes the coupling. So we remember these equations up here from the previous slides. And this picture describes it pretty well. So you have a charge current coming in through a material, and then you see that you have a split between the different spins. So spin in one direction will go to the left, and spin in the other direction will go to the right. And this is, I will not go in, and I don't know, and I will not go into detail of like why this happens, but let's just take it as a law of nature for now. And this is described by this equation actually. And you see this factor gamma. This is the spin Hall angle. So this angle can actually be very close to zero or actually zero, and then we don't have this effect. Then it's just a normal thing. But it describes this connection, this deflection between different spins. And we also have the inverse spin Hall effect. So it's basically the opposite. You have spin currents coming in, and you have the spin polarization deflecting to different directions, and you find a charge current from this. So at least to me, this inverse spin Hall effect is a bit easier to explain and model, so I focus on this. So basically, imagine you have a spin coming in with spin up, it deflects to the left. And you have another spin coming in, same direction, but spin in the opposite way, it deflects to the right. Let's now say that you have a majority of spin down. What will happen in this case? What will happen is that more electrons will deflect to the right, and you will effectively have a charge current. Because more electrons deflect in one way than the other. And yeah, this is the epsilon here is the Levi-Civita, just a cross product notation. So let's then go into the laser pumped heterostructures. So this is a schematic of the laser pumped heterostructure. So we have a ferromagnetic material and a non-ferromagnetic material anode, which are basically layered, very thin layers next to each other. So it's on the nanometer scale we're talking about. We then have a laser beam exciting the electrons in the ferromagnet. And as we know, a ferromagnet will have some more of one spin polarization in general, I think. So basically you get these hot electrons, we call them, bouncing around very quick inside this ferromagnet. And some of them will actually enter the non-magnetic material before scattering. And this will effectively create a spin current going along the Z direction. And let us also acknowledge the fact that we have a very big extension of this material in 2 dimensions and a very thin. So we can basically view this model as one-dimensional. So we have only the Z axis, which we only have variation along the Z axis in this system. So you see the coordinate system there also. The Z axis is what you think will be the X axis. Then we see that we have only spin in this picture in the Y direction. We only have current, like flow, in the Z direction, which give us only charge current in the X direction, because it's a cross-product relation. So spin comes in, and it's affected upwards or downwards. Like this is all the degrees of freedom we have, which in turn will result in an X-polarized radiation field emanating from this thing. So to the E of yeah, some properties. So basically there is like a delay in the system, like the laser coming in, exciting electrons, making them bounce around, creating a spin current. Like this is not happening like instantaneously, and this is the reason to why we can find this this terahertz frequency. So it's basically scaling down the frequency in a sense, because we don't have this. Yeah, it's just a delay basically. You can say it like that. And then you also have polarization. So the polarization will also be linear and perpendicular to the magnetization of the sample. So this also follows from the cross-product relation. And it's also not dependent on the laser polarization. So this laser coming in can be polarized in any direction. It will not make a difference because it will just kick out electrons, and then like the information of the polarization is destroyed from this point. And then, yes, the amplitude of the terahertz field scales approximately linear with the power of the laser pulse. So, okay, let's skip this. Okay, so now to the paper. So we're back here. And so what was the purpose of this paper? So we have this foundation now of the heterostructures, and the purpose was basically to optimize this. So how can we find the best properties of the emitter field? And how can we model the system and understand the mechanisms that make this particular emitter the best one? So we can change now to the frequency domain. So we have the E of omega instead of the E of t. So we're no longer in the transient space, but in the Fourier space. And for all these experiments, we fixed some parameters. So we say that the incident laser is the same. So it's a titanium sapphire laser oscillator with a center wavelength of 375 terahertz and the envelope width of 10 femtoseconds or 100 terahertz. And we introduce our tunable parameters, which is the impedance of the materials, which is Z of omega, and the spin Hall angle. So all of this can be seen in this equation. We don't need to go into detail of this, we can do it later maybe, but this just describes the. And we can also look at the geometry, and we can consider the total thickness of the plate, and also the individual thicknesses of the different components. And maybe we can do some smart tricks also to get an even better result. So they start actually by varying the ferromagnetic material. So what they do is they say, okay, we have a ferromagnet which is 3 nanometer, and we have a non-magnet which is also 3 nanometer, and it's platinum. So platinum is fixed, ferromagnet will vary. And they realize they get very similar waveforms, so very similar frequency dependencies, but different scales on the amplitude of the radiation, which comes out. So we find this. So this alloy of cobalt, iron, and borium is the winner, basically, as you see in this graph. It gives the biggest amplitude of the emitted radiation. And this will now be our fixed parameter for the next experiments. So when determining the other components, like the non-magnetic material, we will always use this one. And yes, so then we vary the non-ferromagnetic material. So what we do is that we do the same thing, but we use this winner from last round as our magnet, and we vary the non-magnet. And also here, practically no variation in the waveforms, only in the amplitude. So amplitude is what we consider in our results. And we actually find this. So we notice that platinum has the strongest conversion to electric field in this sense. And we also realize something very interesting, that you can have different signs of this spin Hall angle. So, for example, I don't know if it's wolfram or tungsten, it's very many different words for it, but this W thing actually has almost a bit around half of platinum in conversion, but it gives electric field in the other way. So basically, if you have a spin-up electron coming into tungsten, it will deflect one way. If it comes into platinum, it will deflect the other way. So charge currents go different ways, but it's okay. Nice. Okay, and then we actually start varying the thickness. So the thickness of the layers. And we find that, yeah, we use this combination, which we found was the strongest, and we start varying the thicknesses. And also here, waveforms are similar. We consider amplitudes only. And they found this thing. So what they thought initially was that it would only scale with the thickness. Like we have more material, we will have a stronger, like a bigger, how can I say, ratio of conversion basically of this incident laser pulse. We will just get more emitter, means more power, I don't know. But this is not what happens. We have actually a peak at 4 nanometers. So 2 nanometer, 2 nanometer is the peak for this thing. So why? Why is this the result, they asked. And they came up with the theory that this thing actually acts as a resonator. So a Fabry Pérot resonator. So you have this, because the wavelengths of the incident pump and also of the terahertz field is much bigger than the thickness. So you don't have any destructive interference. You can approximate it as almost purely constructive, the interference when bouncing around it. But they actually find that at this critical thickness, 4 nanometer, we find that the reflection losses from going back and forward actually like kills the resonator. So you have the resonator giving positive effects until the reflection is too big. So, and that like perfect balance here they found at 4 nanometer. Okay, so yeah, this is the winner. But can we do better, is my question. So I actually have a question for you. Do you have any idea of how we can change the geometry or maybe do something to get even more out of this?
Do they have to be the same width?
No. No, you can do anything. The word is yours. Yeah, Drew?
Maybe process the output waveform somehow.
Process, like have some filter? Or?
Yeah, something like that.
Yeah, maybe.
Can you stack several of them?
Yeah, you can do. This is the right direction. If you have 3 layers, do you have an idea what you can do if you have 3 layers?
What do you mean by better exactly? A larger
It's a bit unclear, but like better, everything better, like better, higher amplitude of the output. Okay, I can spoil if you want to see the answer. So the brilliant answer actually is a trilayer. So in this setup, you actually put the ferromagnet in the middle, and you see that actually the spin current will emanate from the ferromagnet. But due to the different directions, since they have different signs, the wolfram will convert the charge current in one direction, and the platinum will actually convert in the other direction. So if we had 2 platinums, we would have like opposing currents, for example, and then they would cancel. But now they actually amplify each other. So this is something they did, and they actually don't cover like how they come up with the dimensions for this, but then they just say like this is a very good dimension. So we just accept their answer for this, and it's actually the best. So if you go back, maybe, I don't know if you realize it, but this one is not normalized. It says normalized, but it's not normalized. It's because I hide them. They're here. So yeah, you see the trilayers are, so these are the different configuration of the trilayer. So you see they have the best amplitude, actually has 40% higher amplitude than the optimal bilayer. And this is, I said they have similar waveforms, so this is actually the same for all of them, but this is what we find in the broadband region. So we find that we cover almost 30 terahertz of different frequencies, which is very good compared to the others, as we will see. So these are the state of the arts I mentioned before. So this is the Spintronic trilayer. This is the worst bilayer, one can say. It's 12 nanometer. It's some bad materials. It's really not optimized at all. And you see it's like doing nothing, actually. Then you have the gallium phosphide here, which is the one I mentioned in the beginning, like the state-of-the-art emitters. You have the zinc tellurium here, and you have the photoconducting switch here. So these are the contenders, and you can see like the photoconducting switch is better in this region, but then it drops very fast. And this blue one, the zinc telluride, it also has very big inconsistency in the spectrum, although it's a bit better here actually. And the gallium phosphonide, it's a bit better here, but like in general it's just worse. So if we take like a battle and we take all of these three against the trilayer, then maybe it's even. But individually the trilayer wins. Okay, so this was the paper, and maybe some conclusions and summaries. So they found a very wisely optimized terahertz emitter, which is cheap and scalable. So this is of big importance here, because we have some lasers which are way better, but super expensive. We also find that it has more consistent spectrum than the earlier state of the art, as it covers the whole window, 1 to 30 terahertz. And it also incorporates some sort of Fabry Pérot resonator in its, I don't know how to say it. Yeah, it's what it is basically. And this is very speaking. This speaks for a lot of